Hello. It is a new month, which means if we go to current puzzle by Jane Street, there will be a new puzzle released. Yeah, so I haven't actually looked at this puzzle yet, but judging by the amount of people who've solved it so far, I assume this one's going to be pretty easy. Looks like, let's read the puzzle. So you place positive integers in each of the cells, but not all of them, so that each cell contains the digits 1 to n for some n. So we don't know the maximum. For any integer, the cells labeled k must form an orthogonally connected grid, a k-omino. Obviously, if you put 4 4s, then you're going to create some kind of shape that is made up of 4 cells, and the components of that shape must be orthogonally connected. Okay, that makes enough sense to me. Furthermore, for each k greater than 1, the k-omino must contain the shape formed by the k minus 1s. Rotations and reflections are allowed. Oh, that's tricky. So that means that the shape of the 2-omino obviously contains the shape of the 1-omino because it's just that one cell. But if we go to the 3-omino, that means that we must be able to fit the 2-omino in here somehow, which we can because it's straight. And then for the 4-omino, we can see that we have a region of length 3 because the 3-omino is a straight region of length 3. We're rotating and reflecting, or I guess, yeah, we're reflecting and then rotating the 4-omino so it fits in this region. Oh, that's tricky. Alright, let's keep reading. Some of the cells have been labeled, but unlike our previous subtiles, we have used variables to obscure those values. After completing the grid, compute in each row the sum of the labeled cells. The answer to this puzzle is the product of the maximum and minimum row sums. Okay. So what do we know? We know that the numbers 1 to n, some n, which is going to be 25 because there are 25. Yeah, let's just do 25. I think that's probably the safest bet. Anyway, I'm thinking of trying to solve all of these, like put these into a solver. Okay, do I actually remember how to even write Prolog? So CLPZ is a Prolog library or something that lets you do constraint logic programming over the integer domain. We're only concerned with integers, so that's pretty much perfect for us. All we can really say is that each of these is in the domain of 1 to, in this case, we know that the answer is 6. Okay, so this is my list. So let's call it maybe something better, like expers. And then we want to say expers ins 1 to 6, which is inclusive. Oh my god. I think what is stuffing me up here is that I'm trying to use the CLPFD ins clause over a list of expressions. What I need to do is I need to say y is equal to that, and then y in that, and then we can see that it gives us the right result. Insert in, and we can just say expression low high, t is equal to exper, and then t in LH. So now we can label xy, and we get, multiple combinations. So I guess the last thing to do tonight is to put the whole board in. Ooh, I don't know how to do square root. How do you do square root? Is that even possible? Okay, I don't know how to do this. I think, honestly, I would be better off putting this into, like, Wolfram Alpha. Yeah, this is really weird. The expressions look correct. I give up for tonight. Okay, hello. It's a new day. It's 10 p.m. and I started working on this again at 8:30 p.m. So I've been working on this for an hour and a half, and I've gotten approximately nowhere. So I figured out that the prolog that I was trying to code up doesn't work because this is CLP FD, which is assuming that the variables are integers. So if I do x, y is equal to x times 2, and y is greater than 1 and smaller than 4, and I try to label x and y, you can see that the only two options are integers. But I could have had x be equal to 1.5, because 1.5 times 2 is 3, which is between 1 and 4. So I tried Wolfram Alpha, and I tried to basically put in some of the constraints, and I got this answer suggesting that b is equal to 2. But I started to seriously distrust this when I added the additional constraint of b potentially being 6 returns no solution for some reason. I'm actually just now noticing that this says double bar x bar double bar gives the norm of a number vector or matrix. Maybe the whole reason this didn't work was because I should have used ORs. Oh my god. Okay, so this is correct then. So in other words, it's between 11 over 4 and 3, and b equals 2. But I don't think this is correct. If you look at this equation here, square root of a plus 2 over a, you can kind of figure out what the values of a are, because we know that the result of this formula has to be an integer, and it has to be between 1 and n, where n is likely going to be at maximum 25. So if we look for the minimum value that will be equal to, we see a equals 2. And if we increase this any more, you can see that a is less than 1. And obviously, as you move toward 25, that number just becomes smaller. So those two ranges are completely disjoint from one another. So I think the reason is because here I'm assuming that b is positive, whereas we don't actually know that. So let's go over what we know so far. So I wrote this off screen, but that's because my screen recording software broke. Pretty much we know that b has to be an integer because we have b squared, and we know that b can't be 0 because of b squared as well. We know that b can't be 1 because then b minus 1 squared would be 0, which is not allowed in the grid. And we know that b is at most 7 because we have 8 minus b. And then for a, we know that in the log of base anything function, the operand of the log function has to be at least 0. So we know that a is positive at least, which is good. We know a can't be 1 because then this would be division by 0. And we know that a is at most 2 by this function that we just kind of discussed. Now c log function, we can see that c has to be at least 0 because obviously in the base you can't have a negative base in the log function. So now I want to maybe try putting that into Wolfram Alpha now that I know what went wrong. Okay, so this says all values of a comma b are solutions, which I don't understand what that means. Okay, I've also been experimenting with Z3, but now I'm thinking maybe it's just better if I try to look through the possible values and find the value. So basically I want to get the possible values for a here. Solve that for a. Yep. Holy crap. Okay. Def a inverse times x squared. So now if we do AF where a is 2, we'll get 1, and then if we do a inverse of 1, yes, plus 1 instead, please. Okay, this looks good. If I do that, we should get to, yeah, nice. Okay, hear me out. If we look at all values of a one by one and look at all values of b at the same time, then we should be able to see an integer for any one of these. Oh no. Huh? 22.3. No. No. Wait, I'm kind of excited. Okay, let's make a note. This is the first case where we say a is 0.25, b is -3, so that is a legit result, and then this is a fake result. -1. We know b can't be 0 or 1, but if we, might as well try it. B 2, 3. Okay, so b could be 3, and those will probably be the last results. Oh no, interesting. Okay, I didn't want this many results. So looks like A is either 0.25 or 2, and B is one of -3, 3, 4, and 5. So this is good because now what we can do is we can duplicate this tab and we can say with confidence now that B is one of -3, 3, 4, and 5. And when I do this, it should give me the same result. What? Oh, -32. So A equals 0.25 or A equals 2. Constraints. And yeah, it looks like A equals quarter and B equals -3 is the only one that works. So does that make C anything? I think we can figure it out based on this. I think it's either 1/4 or 1/2. Look at this. C plus 2A. We know that's C, so that implies that C is at least a half. I think C is a half. So C has to be in. Let's do this. That's 0.5, 1.5, 2.5, etc. Let's do this. Let's determine the bounds log C 1/4 and C is greater than a half. Whoops, this needs to be between the valid range. That's C is less than 1. Okay. We know that C has to be in the set half, 1.5. The only valid option is half. So C is a half. Okay, so the last thing I want to do tonight, because it's hella late, I want to compute all of the expressions. Okay, let's see. What the hell? -12? B over A. Oh yeah. A squared. Okay, there we go. Okay, so the next step will be to create a view of the board with those numbers populated, and we need to probably create an algorithm to fit the K ominoes. I'm gonna go to sleep. It's like 11 p.m. Hello, I'm back. It is 9 p.m. Also, I switched keyboard because the other one was so loud, so hopefully this is better. Okay, now let's put in all of these locations. Can we show the grid, please? Yep, that looks roughly correct. And instead of this, we want to put in the value, and I think that should be it. That should just work. Yep, looks good, except now we need to round that, make that an integer. Let's do something and say for R in grid, print R. Let's do data, or grid, CSV, paste, and that should be a valid CSV. We'll do get data. Oh, data, yep, next. We're gonna copy this, and then we're going to put borders around this and center it. Okay, and now that's our grid. Okay, cool. So we can compare this with this and make sure it looks right. It should be in 5, that b squared should be in 5, should be 11.5. Oh no, this is again wrong. There. Okay, good. Alright, so this is really the crux of the puzzle, so we can start immediately coloring things in. I think, as with other Jane Street puzzles, the best way to get started probably is to look at the example puzzle. If we look at the 2 omino, there's a few ways we can do it. Given that we know this cell must be part of the 2 omino, the first way to do it is by adding a block here, and then this is the second way to do it. And then we keep recursing, and we say, okay, now we look at the 3 omino. So starting with the same logic in 3, we can say, at each iteration, I can look at the possible cells that I know that are part of this 3 omino and grow them by 1 valid position. This is like a first step. This is also a first step. and this is also a first step. Now, given all the candidates, what's the next level we can go? And one way is here, if we're in this cell. Another way is here, if we're in this cell. And the last way is here, if we're in this cell. I think if we do that, this is maybe not incorporating all the information, because for higher levels, like if we had some weird shape and we grew, one of our shapes into something like this, but we knew the shape had to contain a 4-omino, but we knew that the 4-omino looked like this, then we're missing this extra block that should either be here or here, and this shouldn't exist. Potentially by using this greedy search, I think we kind of put ourselves into too many combinations and not immediately satisfying the constraint, because we would have to check the constraint kind of retrospectively. So I think this is a branching problem, but I think challenge is enforcing the contain constraint. So I'm thinking if there's a better way to build the k+1 omino if you know the shape, or assume the shape of the k omino. This is tricky. Yeah, actually I think this is infeasible. Oh, you know what? Maybe we've tried to fit the 5-omino to the existing 6 cell first. Maybe that actually restricts it more. What if we took this 5-omino, computed the reflections and the rotations, and then for each of those we tried to align, we picked one of the 5-omino cells and tried to align it with the 6 cells. Oh no, we actually don't know that. We don't know that it must align. It just needs to align with the number of 6 cells minus 1. The number of k+1 cells minus 1. Because there's two possibilities. Either there's all the 6s are already on the board, and we align the shape and then add an extra cell. We could add that or that or that or that in this case. Actually, that's not even true. Okay, let me talk through this again. So we have this 5-omino. We know it's here, so this is not free. This is also not free. We know this 2 here, and we know this 4 here. We obviously know this 1. And there are 2. We want to place this 5-omino such that... Oh no, it's not even true. Wait, no. Yes, no. What I thought was that we needed to take this 5 shape and put it on the board such that it overlapped both 6 cells. Obviously, you can see that's not even possible in this example, because we actually need to grow that 5-omino, which has been rotated here. We need to grow it by 1 cell. Okay, yes. We can never have a configuration where the k-omino is placed on the grid such that it excludes 2 or more k+1 cells. The reason is because we can only grow the k+1 omino by 1 from k in order to reach 1 of the k+1 cells. So we can't grow this by 2, because if we grew it by 2, then now it would be a k+2 omino, which is not correct. Okay, so in other words, if we have a k omino, we need to place it on the board in a valid configuration and exclude at most 1 k+1 cell. I think the logic there is pretty sound. Let's look at this 4-omino. We can see we have this 4-omino here. We need to place it in a configuration that works. So this is one configuration. It's a valid configuration for the board, spatially, but it doesn't work because the covered cells exclude 2 5s. We can't grow this to include both 5s, because then it would be a 1, 2, 3, 4, 5, 6-omino instead of a 5-omino. So I think maybe counterintuitively, the smaller the k is, the more combinations there are. And then as the board gets more restricted, the search space becomes smaller, which maybe helps us a little bit. So we can think of it in 2 legs. So we take a k-omino, this 5 in this case. We rotate it and reflect it. For each of those, we find valid configurations on the board. And then once we found a valid configuration, we have 2 possibilities. Either we are missing at most 1 k+1 number, or in the case of the 5-omino, we could either take this cell, or this cell, or this cell, because they're all adjacent. So I think that's the crux of the logic. Well, whatever. Let's try it. What the hell? I don't even see a common difference between these. Okay, nice. So this is rotation, and this is vertical reflection, and this is horizontal reflection. So let's go ahead and encode this shape. Wait, what? Hang on, how did I arrive at... that literally does not make any sense. Hello? What the... What? Oh my... Dude, what is going on? What the hell? I can't even switch tabs and stuff. Oh, I'm actually so done. I think that has to be right. I have very little faith in this working now. Okay, these seem to be working now. So all that's left is to implement the rest of the logic. Okay, well, that took me a very long time. I think I'll come back tomorrow. Hello, good morning. It is the next day, and it is a gorgeous day, so of course you know there's nothing I'd rather be doing than sitting inside. Okay, so last night we pretty much left off with this idea that given that we knew the previous k ominoes and we were looking at 5, then we would essentially be taking that 5 omino and finding all of its permutations, and then we would just take the unique shapes of those and iterate through the grid to try to find valid positionings. So in this case, one valid positioning might be like this, another valid positioning might be like this. So how do we define what a valid positioning is? A valid positioning, as we know, cannot be... Oh no, something has gone wrong again. Oh no, this looks familiar. Oh no! So the question becomes, what is a valid positioning? We take the 5 omino shape and we rotate that 4 times, and then we take the vertically reflected shape and we rotate that 4 times, and then we take the horizontally reflected shape and we rotate that 4 times. Now you can see here this will yield, I think, only 4 unique shapes. So what is a valid positioning of a k-omino in the board? Well, we need to ensure that nothing goes off the grid, so you can't put the k-omino here. The second condition is that k-omino can't overlap, so when we're laying out the k-ominos we can see like one reflection of this shape is, if I use brown, this, but this isn't allowed. I don't know why this browser is like actually dying every 5 seconds. Okay, this is good. If we ever place a k-omino and it excludes more than one k plus 1 cell, then we know that we've placed it incorrectly, so it's not a valid candidate. Okay, I think with that I'm ready to get started. I'm gonna do something maybe a little controversial and open up my friend Claude, and I'm going to ask it for a visualization function to visualize pieces on a board. Oh my god, alright, this is huge. Yeah, that looks great. Oh, wait, no, I don't understand. Okay, something's wrong. So that's 0 rotations, that's 1 rotations, that's 2 rotations, and that's 3 rotations. What are the valid candidates? Well, so we can do rotate k-omino I for I in 4. We need to do the same thing for the 2 reflections. Yeah, so I think like 9 and 7 are the same in this case. So what we want to do actually is... Okay, I think we need to do lex sort. So now if I do this same thing for the 9th candidate, which we know is the same shape, we can see that's the same. So now we can finally do what I was trying to do the whole time. And we should see 8 distinct shapes. Yeah, that's going to cause problems, I think. Right now, we're considering 0, 0 to be the bottom left of a shape, but in reality, it should be the top left of a shape. Oh, that's so annoying. Oh my god. Yeah, this is an issue. Okay. What are all these 4s doing? Oh, right. Okay. Is this working? I actually can't tell. Where is the original shape? Yes, it is working. Except that's counterclockwise. It's okay, it's okay. Okay, so this is kind of going to be our get valid positions function. To determine the layout of the k-omino offset by RC, the first thing is it off the map. Actually, we can do this here, and we can say if k plus r0 is greater than or equal to r, break. So that's basically saying if the current row offset is too large, it means we fall off, stop searching. We need to check, do we overlap with any positions that are not equal to k plus 1. So if not 0 or x grid empty, then we break. So we can check this logic. Maybe we can do an any, because I feel like an any will be slightly more performant. So now we can yield the same thing with this. So at this point, we're on the grid and not overlapping with anything illegal. So the next step is to count k plus 1 inclusions or exclusions. Imagine we have something called labeled counts. So this will give us 2 if it was 6. The labeled counts of k next minus kcand inclusions dot sum, or sorry, equal k next dot sum is less than or equal to 1. So now there's 2 possibilities. So if k next exclusions greater than 1, we have to break lf exclusions equal 1. Then we need to make sure that one of the adjacent cells contains the excluded cell. So how do we even do that? I don't know. Otherwise, we're obviously equal to 0. Now let's do visualize. Okay, why is this not working? Oh, this should be pass, and this should be pass. Okay, and so we can see all of the what are supposedly valid shapes, but this is not true. This should be continue. I don't know what I'm actually doing right now. We should continue. Okay, so now there are no valid solutions, which makes sense. Let's rotate this so you can see, it only found one position. That's really good. All right, I'm gonna take a break, and when I come back, I'll implement, I think, these 2 pieces of logic. Okay, I'm back. Let's implement this thing. So pretty much we know that if the excluded k plus 1 cell is not within if it's not 1 cell away, then we're in trouble. So, okay, in this case, what we're gonna do is we're gonna say get neighbors. So in this way, what we can do is this will give us all neighbors, and then we can say match on all the ones that are 0, and then all the ones that are 6, and that will give us whatever digit we are looking for. K adjacent cells equals set get neighbors match equals k next. If len k edge cells equals 0, then excluded k plus 1 cell is not in solution. So this way we just continue. Otherwise, no, that won't work. If we call this function get neighboring cells on this cell, then we'll return 6, but we don't want to take this 6 because this is already part of the shape. What we need to do is we need to do a set minus. So now this logic should work. Okay, kcand, so kcand equals kcand.append, and then np array k edge 0, k edge 1. And I think we want to do like valid k1 equals nothing, and then we can do valid k1s plus equals kcand. Whoa, okay. Oh yeah, I need to flatten this. So that gives us what we expect. Can this just be a set? Yeah, cut that and put it in here. Let's actually try this for the rotation, and then we want to offset it by, what does that look like? 0 rows and 1 column. Why did that not work? Because that, yes. All right, so that shows us that that's working. We still need to do this. So in this case, what we'll say is if we reach a condition where we've captured all of the k plus 1 cells, then for k add cell in k add cells, we will add the cell. So for A, B, and K add cell, valid K's plus equals A comma B here. That's done. So now we can do, okay. All right, that shouldn't happen. Move that. Yep, so that's the only one that we found. So now we want to try this on 4 omino. So this is basically saying we want to fit this shape in here somehow. I assume there will be a lot. What I might do is look for the sorting mechanism that we used here. I might bring this into its own function. So this is like basically a way to add to a list that's sorted. 4, 5 it should be. Yeah, so there are a lot of combinations. So that's definitely real. That's obviously the true one. That's kind of the reverse. That works, that works, that works, that works, yep, that works, that works, that works, and that works. So now I pretty much have the list of 5 ominoes. This is a list of candidate 5 ominoes. So what I want to do now is I want to propagate the change. I need to figure out a way to, given a board and a k omino, propagate and branch off into the k+1 omino. Okay, so I've put this in language that is a little more understandable. The first thing we need to do is have a list of k omino candidates, and for each of those we will fill in the board with the appropriate k's. So for example, for this candidate we would fill all the blue cells with 5s, and that would become our new board. Once we fill in the board with 5s, we're ready to search for the k+1 omino. So the way that we do that is the algorithm that we've just come up with, which is create all rotations and reflections of this and try to place it in the board. But before we do that, we need to make sure it's centered at 0, 0, otherwise we'll already have an offset, which is not allowed. So we're going to need to find some way to take the maximum across the rows that we can shift up to 0, and then the maximum across the columns we can shift down to 0. And we'll use that shape as our base for the k+1 omino and then run the algorithm to find all the candidates. And then we just branch and repeat from that. So the first thing that we need to do is we need to fill in the grid. Then we need to reposition k omino, and we can do that by minus equals np.min k across the rows, and then we can do k across the columns is np.min k across the columns. And then we need to run algorithm, and now we will start the recursion. Oh. Oh, yes. Yes, yes, yes. Okay, so that looks like it worked. I have 2 concerns now. I think this will be very slow for the full puzzle, and I don't even know how we can build up from 1. We need to start the assumption that we know the 1 omino, which we do, and we need to build the 2 omino. None? What? I actually think something might be wrong with the algorithm. Now, k adjacent cells is the get neighboring cells. X grid empty. I knew it would come back to haunt me. Why did I leave it in there? If we now remove that statement and add back the return statement and try to visualize the grid. Oh, hang on. I want to go up to 6, please. Yep, okay, we solved the puzzle. I think this is going to be very, very slow. Nevertheless, I think we have to try it. Yeah, let's just try that first. That looks correct. I think 15 and 16 might be a little close to each other in terms of their colors. Visualize shapes, so this one. Okay, I'm scared. As expected, it's taking a lot of time to run. Looking at the grid now, I feel like it will probably not find a solution. The number of combinations, like the number of possibilities for the small k ominoes is so large that I think if you try to branch out, especially at the small numbers, then you just lead to this recursion that is not even deep, but so shallow. Like there's so many branches to explore. There are so many ways to configure the grid at the beginning. It's only at the end when it becomes restricted. So you end up like going really deep, and choices in the end game are very limited. But at the start, because they're so massive, you have no idea kind of which path is the right one to follow. But I'll leave it running for a bit and come back probably in like 10 minutes. Alright, I am back. As you may notice, some time has passed. I actually went outside, if you can believe it or not, on this chilly winter day, And I tried to think of a more efficient solution, but I couldn't really. I think what we're doing right now is kind of the most restrictive way that you can build the grid from the bottom up. I think I will try maybe like a last ditch effort. I did have one brief idea, which was to fill in some additional squares. So for example, you see this 6 needs to connect to this 6. And if we had the case where this 12 created a bridge here, that would lock out this 6 from ever reaching the other 6. And if we had the 12 come over here like this, then that would lock out the 11 from reaching its buddies. So we must have a 12 in this grid, or in this cell, I should say. So that's just one example. I think what I'll try to do is populate as many as I can by just looking at what needs to be true, and if that doesn't work, then yeah, I don't know what I'll do. Looking at the 9s, this one is maybe interesting. So if we look at the 14, we can't really have a scenario like this, because then the 14 would be like locked in. Oh, sorry, the 9 would be locked in. So we have to have these two 9s connected somehow, which means that the 14s either go over here or here, and because if they went around the 16, that would lock in the 16, then we know, I think, that that has to be a 14 as well. Now this 12 is kind of interesting, but not really, because that's fine for the 4, like the 4 could still be that, and that's also fine for the 4. Actually, that's a good point. This 12 here has to be connected to this 12, and this 12. That's actually not uninformative, because we know that the 12 cannot come down here like this. Actually, oh no, even doing that is illegal, because then the 6s are separated. So the 12 can't come down here. So this 12 has to reach that 12, although we could have a case like this and then a case like this. So that's possible. We could have this as a 12. If we did have something like this and then that, like that would be allowed. But that's such an irregular shape. Oh, it's tricky. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 12. 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. Okay. Does that help me with anything? So it's one or the other, basically. So that is one path. And what about option 2? Wait. Okay, time to implement the third option. 16, really? And then there's one last option, 16 as well. I wonder if for each of them I can try to take it to 14. I think this is wrong. Okay, so we've disproven this. This is progress. This is progress. Okay, so I did a lot of this in silence, but I essentially tried this option, which is the red line. You can see that the 12 comes down and around the 4. And if I run this until 16, it provides this solution, and it says this is the only solution. But you can see two things. The 3 is cut off and the 4 is cut off. So that tells us that this option is not allowed. So let's try this option. So this option is allowed. Oh no, this option is not allowed because the 7 is cut off. Dude, I'm predicting that all 3 of... I'm predicting that all 4 of these options are all going to lead me to conclude that none of them are allowed. Oh, I see. There are no next steps after that. Okay. Oh my god. So it's literally all writing on this. Okay, so if this produces something that's wrong... Oh, far out. Okay, now I want to check the spacings again. Yeah. Okay, so the spacings look correct. So it's not the spacings. Those are the only possible ones. That has to be correct. This is really strange. Is it possible that that's not a 14 there? I don't think so, right? Because the 9 has to go through there. I'm worried that I've broken something, and because of how complex this is, I won't be able to see it. I don't know what to do. I mean, that was kind of my last hurrah. I wonder if I've swapped around those two equations. I don't think so though. Oh, it's all correct. Okay, hello. I regret to inform you that I am back. I honestly have no idea what would be wrong with this. Like, I've been thinking, I really don't know what could be wrong with this. Something did come to mind, which was maybe I'm just returning. This return statement is like cutting off the other solutions. So instead, why don't I just do this and then do sols plus equal g, and that means I don't even have to do this return statement anymore, and that won't be anything. And then I put in sols here. I think that's fine. So now just run that, and then I think that's okay. Okay, let's see. Oh dear, something must be wrong, I think. Okay, no, I think it's right. Oh my god, are there really just that many solutions for that? Holy crap, wait, that's insane. We'll see. Okay, this is better. What is this? What am I looking at right now? Oh, because I'm visualizing shape here. So now if I run this, it won't print anything. I also want to do print number of solutions. So here the solutions is 0. Oh dear, this looks like a lot. Number of solutions is 10. Wait. Oh, okay, so it's working, Okay, so this one is false. Can't have that. I think this one is also false. That one is not possible. 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 This is the first one that is possible, because we have a 3 region here. We have space for the 7 and the 2 and the 4. So that one's okay. This one's not possible. So does that mean that out of all of these, only a couple are really possible? So let's count the number of ones that are possible. 1, 2, and that's it. So really there's only 2 that are possible. Now let's try this. So again, this is not possible because of the 4. This is not possible because of the 4. This is not possible because of the 4. Not possible because of the 4. And not possible because of the 4. That means we've narrowed the final grid down to be one of those 2. This is potentially correct. So we can write down 1. 8 is possible and 9 is not possible. So it's 3 and 9, or 1 and 8. I think we know this, the 3 omino, right? That shape. So I'm wondering if we take sols 1 and we do something like this. 3 omino is forced, and therefore 4 omino is implied. The number of solutions is 0. Oh, I messed up. Let's check. 4 looks right, 3 looks right. Now we have to pray that the 8th solution will work. And if it doesn't work, then we're back to square one. Oh! Okay. Oh, you know what? I just realized. It's because I'm doing that, I think. I need to give it G. This is so messed up. Like, oh my god, are you serious? 643? How? How can there be that many? That doesn't even seem right to me, because if I go up to 16, will that reduce it to 1? It does. But how? How is that? Oh, no. So that's allowed. This is allowed. But now if we do 1, if we do sols 1, I have a feeling that the result will cut the 2 off. Yes, yes! Finally! It's about time I got an answer. Okay, so we now know that the right path is 8. We should now be able to come up with the answer. So after completing the grid, compute in each row the sum of the labeled cells. Answer to this puzzle is product of the maximum and minimum row sums. I say row sums equals, so that must be a 2. So G equals sols 0, G, what is that? And now we can plot that, which is what it looks like, and then we can compute the row sums, which is equal to g.sum, that's right, and then we can do row sums.min times row sums.max. And that should give us the answer. Okay. I'm gonna go do the dishes, and then I'm gonna come back and make sure that everything looks okay before I submit. Alright, it's been a while. I got kind of distracted. So yeah, visually looking at everything, it looks correct. The 5 omino feeds into the 6 omino, which feeds in and restricts the 7 omino so that the 2 omino has to go there. And then that's the add-on. Yep, that's the 8 omino, and that's the extra cell. Alright, let's submit. Alright, that must have taken me, if I had to estimate, probably a whole day, probably like 12 hours. But yeah, that was tricky because you had to figure out the constraint of a k plus 1 omino containing the k omino, which is not very clear how you kind of do that. Hope you enjoyed watching me, and we'll check back in a couple days to see whether my name has been added to the leaderboard.